How's it going, everybody? In this video, based off the title, we're going to be covering a high-level overview of firewalls. So let's begin. So what we're going to be focusing here on and discussing is going to be the nature and the need for the firewall and how they actually come and how they work. So we need to understand some things about firewalls before we really dive into the crux of what they do and why they're needed and all that type of stuff. So the firewall, in no lacking effort, is designed to block traffic, right? And at the end of the day, there's multiple types of firewalls, and there are whether it's physical, virtual, whether they're managed in-house, like through a command line or some sort of GUI, or if they're cloud managed. They need to be interacted with in order to do their job. Now, you'll hear a term called defense in depth. Now, all that simply means is, let me go ahead and adjust keep my pen pad here so I can write a little cleaner. You'll hear defense in depth. Now, all that means is layered security. So you'll talk about a firewall right here at the edge. Then you'll have potentially another one here on the PC to prevent things that get passed through the infrastructure firewall, the application firewall. You'll catch it with like AMP for advanced malware protection. Then you'll have other ones that'll be in your virtual environment. So you have a server over here, and maybe this guy's running ESXi. So you have an ASAV deployed over here, which is actually what these guys are here. You can deploy these down here and in your virtual environment to control how your virtual machines communicate with each other. So there's a lot of cool stuff that comes into play with how they work. Now, there's the option of a routed firewall or a transparent firewall. Now, what's really the difference? Well, this guy here is layer 3, and this guy here, transparent, is layer 2. So you're dealing with it at the VLAN level versus at the IP level. So it still deals with IPs, and we'll talk about that later on. So just in context, the way that I'm planning on building out this course, or these videos I should say, is this guy right here will be a routed firewall, and this guy will be transparent. And that's the goal. This guy will be an HA box over here, or an HA pair, I should say. So that's basically how this comes into play. Now, as we dive into this a little bit further, we need to put some constructs out there, and I'll whiteboard as I'm going along to try to drive the point home. But you have to understand where and how the firewall gets deployed. So if we take a look at router 5, over here there in the lower left-hand corner, you can see that the line drawn is drawn on the right side of the firewall, where what would essentially be the internet. Now, when you start to break up the firewall into different domains or security zones, if you will, they need to be understood as to what that zone is doing. So on the outside facing the internet, that would obviously be your untrusted zone, because you don't know who is out there, you don't know what they're doing, how they're operating, any of that information is unknown. Now, on the flip side, on the gig 0/1 and gig 0/2 side, there is the inside zone. So this would be the zones facing your internal LAN and things like that. So this would be your trusted zone. So you obviously are going to have traffic flowing from the trust to untrust, or in ASA terms, as is commonly done, inside to outside. However you denote the differences is up to you in your architecture or your design. I will be using inside and outside as I progress through. Now, we're talking about ASA, but this still applies to routing on a router. So down the road, we'll talk about zone-based firewall, and the same concept will apply, inside versus outside, and etc. Now, when you are dealing with the security domains on a firewall or security zones on a firewall, the logic that you're trying to achieve in most cases is that firewall will be the only path out of the secure network. So you're not going to have an alternative path the other way around or anything like that, or no backdoors per se. and then the firewall is going to be positioned in a place, in this case here router 5 or ASAV1 or what have you. They're positioned in such a way that the traffic that they need to enforce has to pass through them so that they can enforce the policies, not going around it or any other direction besides that. So that's basically the idea that we want to come up with. Now, the other thing too to keep in mind is that's data plane traffic, right? That's traffic flowing through the firewall and not to the firewall. And there's a big difference between through and to. So let's just kind of put this into context. If I need to get to the internet and I'm sitting at PC1, which is currently turned off, I need to go through router 5 in order to get there. Now, in that particular case, that means there will be through traffic, right? Now, if I'm on, let's say, I'm on the PC that I'm recording on, and I need to interact with router 5, but I want to connect into it via SSH or Telnet or SNMP, I would have to connect to the router in order to interact with it. Now, that's one common way of doing things, and that's the option to where you're going to be pointing your traffic towards the router is going to be responding to that, or the firewall in this case. Now, that's in cases like that is very common for small branch offices. So what if you have more than one, you have a larger location, and you have multiple edges to connect to the internet or other types of transport. Well, then you would need to take that thought process and scale it. Now, we're going to be talking about this a bit more in detail later, but this is more of a high-level overview of what the firewall is and why it's doing what it's supposed to be doing. Now, the idea is when we're talking about security domains, zones, things like that, we want to remember that the firewall is the border of every security zone that is designed to be operational in the network. And the thing that keep in mind here is when the firewall is the border of the zone, you need to make sure that you keep that zone aspect, keep that in mind when you're building your firewall policies. So you don't want to allow traffic that doesn't belong in one zone into another zone, and traffic that does belong going between zones, that you've put the appropriate policy in place in order for that traffic to be allowed to pass through. Now, we're going to talk about that more in detail later when we talk about access rules, where we talk about going from a high security zone to a low security zone, and then the low security zone a low security zone to a high security zone, and stuff like that. So an example of that would be going from PC1 to PC2. We could have, zone-based firewall configured on here to where PC1 can't talk to PC2 unless it's RDP or some other type of communication. Same thing over here with ASAV1. We could have here gig 0/2 is on the LAN, and gig 0/3 is the DMZ connecting to server 2. So we can carve up the network however we really need to do it in order to operate. Now, another context that we want to talk about real quick is the concept of splitting up the firewall. So let me go ahead and pull up my pen pad again real quick. And let's go a bit thicker. And let's just say for the moment that we have, let's say we take, that's a horrible line. Let's say we take a line here. Let me make it red so it's easier for you guys to see. So we take this line here, we draw it on ASAV1 at the top, and we draw another one, a line right down the middle. Now, on this side here, the top half, this would be considered to be the outside, right? And the left side over here would be considered the inside. And then over here we have the DMZ. Now, if I want traffic to be able to flow, and the default path is traffic can flow from in to out, this way. Traffic can flow from in to DMZ, this way, and from DMZ to out without a problem. Those are the three default flows that are going to work by design if you have implemented a security design where, in this case here, this guy is a security level of 100, this guy is a security level of 0, and this guy is a security level of 50. All the number indicates is how to interpret the security zone. The higher the number, the more secure the network is. Now, what's not allowed by default, and I'll put this into orange because I'm kind of dumb sometimes and I use the wrong color for permitting traffic, is traffic is not allowed to flow from DMZ to internet, or I'm sorry, inside. It is not allowed to flow from outside to DMZ, and it is not allowed to flow from out to in unless it's been specifically permitted. Now, here's the thing. If I have a situation where I'm going to be communicating from in to out, and I have return traffic, let's say, for instance, I need to go out to the internet on test 11 needs to ping Google as a test. That's going to work out just fine. Now, the return traffic is going to come back in and hit the outside interface of ASAV1, but what's going to end up happening to it? Is it going to be permitted or is it going to be denied? Well, it's going to be permitted. And the reason why it's going to get permitted is because the traffic was allowed out first. It came in on the inside, was able to egress or pass through the firewall and leave out the outside. Now, that's going to build a connection in the connection table. It's a state table. It's a stateful connection. And then when the traffic returns, as long as it matches the reverse of the outbound flow in the connection table, it's going to hit the outside interface. The outside interface is going to look at that and go, oh, well, you just left. Now you're coming back in. Let's check the connection table. Oh, okay, so you were a solicited request. All solicited means is traffic from the inside asks for traffic on the outside. So test 11 tried to ping google.com or tried to telnet to R2 or whatever the case might be. Now, an example of an unsolicited request or something that was not is trying to go from a low security zone to a high security zone that was not already executed would be R1 trying to talk to test 9. So R1 tries to go in and do a telnet connection or whatever it might be, or SSH to test 9, but can't. It's going to be denied by default because there wasn't a connection from test 9 to R1 already there. Now, you can permit that with an access list. That would work all day long. But it will not work if it wasn't solicited from the outside, or sorry, from the inside. You'd have to explicitly permit that with an access list. So this is why I mentioned in the previous video that the flow needs to make sense. So to me, it didn't make sense to put NAT before access list because you need to have an access list in place in order for NAT to work, especially if you're talking about from outside to inside NAT. If you're talking inside to outside NAT, you don't need an ACL. You need an ACL to match on the traffic. If you're doing, well, that's not even true either. You need an object to match on it. But that's a discussion we'll have more in detail later on. But these are just some of the variations that come into play that you need to keep in the back of your mind. Now, with that being said, when we talk about how separation comes into play, this is really what needs to be understood. You need to understand if the firewall is going to be the border of your network. You need to understand what the firewall's role is when it comes to that traffic, and is it going to be able to, does the firewall have the feature sets that you need it to have in order to do the job that you need it to do? Now, that could be as simple as an ACL or some sort of advanced inspection, whether it's layer 3 inspection where you're doing TCP and UDP ports, or if it's a deeper level, like you're trying to allow traffic from low to high, where server 2 is trying to open up a telnet connection to test 9 but can't, or open up the web page of test 9. So there's lots of little things that come into play that need to be thought about when you're going through this process. Now, there's also the how do you implement the policies as you're going through here. So you've got a low security zone to a high security zone. You put the ACL in place. Now, you could put a permit IP any as the access list inbound, and it's going to allow the traffic to go through. that would be what they refer to as a permissive access list. So all traffic is allowed by default, and if you want to block it, you need to put something more specific ahead of it. Meaning that if I have a security policy that reads something like this, where I have, let's say for instance, I want to say permit IP any right here for traffic coming into the inside or in on the DMZ, but permitted to go anywhere. Well, it's going to be permitted. But now if I want to block server 2 from being able to open up a telnet connection or what have you to test 9, I would have to type in deny. So deny TCP from a source of, let's say, server 2. But in this case here, this would be me demonstrating using an object in an ACL, which we'll talk about in access control, to test 9 using another object if it's equal to 23. So I want to deny server 2 from being able to reach test 9 if it's going to port 23. So I want to prevent server 2 from being able to telnet to test 9. That's effectively what I would say. Now, if that particular traffic flow was detected, it would be denied because there's a deny statement that goes along with that. And that's one of those things where it's permissive. And then you block explicitly. Now, there's the other way of doing what they call the permissive access control is referred to as the whitelist model, where you whitelist everything and then you selectively blacklist what you don't want to allow through. And then you have the restrictive access control, or the blacklist model, where you deny everything and then you only explicitly allow what you want through. So the logic would actually be reversed here. Actually, I'm going to have to go ahead and flip over to the... It's going to let me do it? It's not going to let me do it. Oh, there we go. I was afraid it wasn't going to let me erase. Let's see, is it going to let me switch back? No, it sure is not. Okay, well, I'm not going to monkey with it too much. Let me go back to the pencil. So now in the other flow, let me go ahead and go back to Reddit. It'll be easier for you guys to see it. In the other direction, I would do a deny IP any, and then I would put a permit in. So up here, I'd type in permit TCP from server 2 to test 9 equal to 23. That would allow traffic from server 2 to talk to test 9 if it's equal to telnet. And that would work. That's just doing the reverse path. And then you would have to selectively allow traffic. I'm going to go on a limb here and say most people are going to want a permissive access list and then lock it down as you need to. Unless you work in an environment where a restrictive model is required based off of either industry or regulatory compliance. So that is my expose on that. Now, when we talk about stateful inspection, we need to understand what it is that actually means. So we talked about it briefly, but we want to go into a bit more detail. So stateful inspection simply means that you're keeping track of connections or sessions on an individual basis as they pass through the firewall. Now, the firewall is going to maintain a table called the state table that's going to keep track of these entries as they're coming through. And as they're coming through, it's going to take a look at multiple aspects of the flow. It's going to look at the TCP and UDP and the source and destination ports, source and destination IPs. So basically the layer 3 and layer 4 tuples that are specific in the transport. So it could be TCP or UDP. So technically it's a 5-tuple lookup. Now, this is what they commonly refer to as layer 4 inspection or layer 3 inspection, depending on how you want to look at it. Technically it's both layer 3 and layer 4. Layer 3 is the IP addresses. Layer 4 is the transport and the ports that are used. Now, as you're going through, you're going to have to understand that this only works so far. Because just allowing, say, server 2 to talk to test 9 via HTTP, that's technically a layer 4 lookup. Layer 3 and layer 4. Because you're defining the transport, TCP, the source and destination IPs, so server 2 and test 9, and then the source and destination ports. So like 33,700 to port 80. Now, you've laid all that out. Now you need to understand that you may not want server 2 to be able to download or look at something specific. For instance, you may not want server 2 to be able to run specific commands or access a specific web page on the router. And in order for you to do that, you need to elevate yourself to what they call application inspection and control. So this is going to be your layer 7 inspection, where you take it above and beyond and you say, you know what? We have to look at what's actually in the payload. So what that means is there a file, and if we reverse the path, if we were to look at, let's say, go from server 2 to, let's see, what's a good example here? Let's say if we were to go from, I don't have a PC to a server connection, but let's assume that we go through, I don't have a good example. Let's say PC2 comes through ASAV1 to talk to server 2. So it goes from over here, goes across up here, comes back down, hits ASAV1, hits switch 1, switch 2, and then, switch 7, and then hits server 2. Server 2's got an executable that it's sitting on its web page, and it's a download. It's a small install file of some sort. Or it could be a PDF. It could be some sort of document. It really doesn't matter what it is you're trying to gain access to. The fact of the matter is you need to be able to go through, and the ASA needs to be able to say, okay, what is it that I'm seeing? I know it's a web connection. I see port 80 and TCP and all that stuff. But other than that, I don't know. That's where layer 3 and layer 4 inspection stop. But you need to take into account the deep packet inspection and the application layer filtering. So deep packet inspection, so let's try to qualify these a little bit. So you may not agree with my interpretation of how this works, but this is basically how I interpret it. Is application layer inspection takes advantage of layer 3 and layer 4 information. How does it know that? It knows that it's TCP, or I'm sorry, it knows that it's web traffic because specific attributes have been seen. TCP is the transport, and port 80 or port 443 as the destination port. It's able to glean that information from layer 3 and layer 4 information, specifically layer 4. But deep packet inspection is not able to be done because you don't really know what it is that the user on PC2 is trying to do on server 2. So in order to do that, you need to be able to take that a step further and be able to write a signature or a filter that says, okay, if PC2 tries to access server 2 and download a PDF file or tries to execute the get command on a specific attribute on the web page, whatever that might be, then you need to go ahead and deny that from happening. But that's deep packet inspection. That's being able to look beyond the protocol information and be able to look at what the actual three-way the three-way handshake has been completed via TCP. But the application inspection has not been done because you don't know what it is that the endpoint is trying to do. Now, you may or may not agree with me on that interpretation of the differences between the two, but that's basically how I have kind of made the determination of which one's which one is which. Now, there's other ways of blocking traffic too. There is the always on IPS, or intrusion prevention system, which is going to look at something, which is what I basically was explaining in the just a moment ago, where PC2 tries to access something on server 2, and you have an application level or a DPI inspection that's happening, and says, okay, well, PC2 can't download anything from server 2. It can just view the web page. That's it. And that, in a situation like that, then that would be taking it a step beyond, and that would be IPS. That would be actually blocking the communication and looking at the actual DPI, deep packet inspection data, and saying, okay, well, you can't do that. That's against the rules. There's other things that come into play too, where you can have behavioral aspects of things too. It's how things have behaved over a period of time. Whether maybe there's a hacking attempt. Maybe server 2 or PC2 is trying to talk to server 2. The connections come up. Let's say it's a remote desktop connection. And PC2 is trying to access server 2 but doesn't know the username and password. So you can look at multiple failed attempts and go, okay, well, why is it failing? Then you have to rip apart the payload and go, okay, well, he's getting a bunch of bad username and password responses. So he's done this 10 times in the last minute, so it's possible that he's trying to hack server 2. So let's go ahead and drop the traffic. That's behavioral. The other one is going to be the application layer gateway. So the ALG, as it's commonly referred to, where you have a client and a server, and you're trying to, for instance, this is very popular with voice over IP communications, especially with SIP, Session Initiation Protocol, where you have a SIP phone that sits at a location, but the call manager that the phone has to register with to download its configuration and things like that is elsewhere. So let's assume for just a moment that test 11 in the bottom of your screen is the SIP phone, and server 1 sitting up here in the upper right hand corner is your call manager. So the traffic has to flow through ASAP1, go out to the internet, communicate back to server 1. Well, let's just for the moment assume that CSR 1 and 2 have been configured to allow that traffic to pass through. So server 1 is actually getting it. Unless ASAP1 has been configured to allow data to flow through it like that, then it could potentially block the traffic. So it's going to go look at it and go, oh, well, it knows that it's SIP because it knows TCP and UDP ports 5060 and 5061 are traveling through it. So obviously this is a SIP phone trying to go out and register with the call manager, wherever that might be. Now, the DPI could come into play here and go, okay, well, I'm seeing, because SIP works very similar to the way web works, and there's a lot of communication that's sent back and forth that you would need to be able to interpret and go, oh, okay, well, he's trying to register, and there's a phone call going out, you see the invite, and you see the 200 okay, and stuff like that. A lot of that data comes through, and you need to be able to interpret what is actually happening with it. So that's some of the things that come into play with it and how it operates. So that's more or less a high-level overview of what comes into play with the overview of the firewall. So that's just some of the basics to firewall overview, an overview of the firewall and how it comes into play, and how you would need to interpret what it's doing and why it's doing what it's doing. So now, I don't want to go. We're at the half-hour mark. I don't want to bore you guys to death, and I do not want to do PowerPoints. And this is just more or less my understanding of how stuff goes and how stuff works. So there's that aspect of things. So without any further ado, we're going to cut this video, and in the next video we're going to talk about some of the ASA capabilities and how it works, and dive into some of the capabilities it's able to support, whiteboard a few of them, and then go from there. Until next time, guys, thanks for stopping by, and we'll catch you guys in the next video.